Well, here's the idea. We're going to investigate this limit idea to a whole new level. And our current definition of a limit, we use phrases like as x approaches zero, the output gets closer to some limit value. Um, the reason why the way we talk about limits is problematic is because we wonder how close to zero do we have to get? I mean, I don't know about anybody else here, but I'll never forget when I first started doing limits. When I looked at table values, and by the way, we didn't have the calculators you guys have, so when we looked at table values, we had to make our own table values. You know what I mean? But second of all, I it always bothered me that we would go like say we go 1 and then point 0.1, then 0.01, then 0.001, and then we'd say, okay, well we're close enough. Close enough? I mean, you could get a lot closer to zero than that, right? I mean, you could. And as soon as you say, well, that's close enough, really? Are you sure that that's close enough? Because that's still a ways away from zero. I mean, you could get a lot closer than that, can't you? In fact, my argument was, shouldn't you be able to get 1 over infinity close to zero? And so that's kind of what we want to try to think about. And so this is going to be our example that we're going to use. We're going to look at this function. Is that what everybody has typed in? And we get that graph. And so my question is, as x approaches 0, what is the limit? Can you tell? No. Okay, so thank you. So the graph looks like this, okay? All right. And why is it difficult to calculate this limit? Because the function has, we'll use a very non-math term, has crazy behavior. I mean, it's really difficult to see what's happening with that function as x gets close to 0, isn't it? So Carter had an idea, and this is what we want to focus on. If we want to be able to find out what happens as x gets close to 0, what should we do? You want to zoom in. Okay, let's do it. Zoom in. I'm going to grab number 2, and I'm at 0, 0. I'm going to zoom in. All right. So Carter, you want to take a guess at the limit? How about we zoom in again? You feeling pretty confident about the limit there? It's hard to tell on that one, isn't it? What are we going to do? There's a limit. There's a limit. You can find it. What's another option? Thank you. Actually, zooming out would be an option, but really I kind of want to adjust the window here a little bit. Um, let's go under our table and let's see what we can create for a window to get a better view of this graph. Because this is what the graph looks like from a certain vantage point, but I wonder, like, what does the graph look like right there? You know what I mean? Like, maybe if we could focus in on a certain spot, maybe we'd see better what's happening. Let's see if we can see what maybe a good box is to look at. So let's get close to 0. What will give us close to 0? What do you want? Okay, 0.1. Ooh. Anybody want to take a guess for what they think maybe the limit is? Infinity, you say. Okay, you say 0. 4,800. 48.64. Now it's starting to kind of narrow in. Okay, maybe $5,000. Okay, now Spencer, you said 4,870.5, but you didn't say that until we got pretty close, right? So you weren't confident enough to make a statement about that until we got to like, a window where this was 0.0001 and this was negative 0.0001, right? And then if you look at the Y values, we're around like 4,870, right? So like this value up here could be 4,871, and then down here it could be 4,869. I'm going to create that window and see if that really gives me what I want. X minimum of negative 0.0001 and an X maximum of 0.0001, okay? And then a Y minimum of 4,869 and a Y maximum of 4,871. We'll see if this contains the part of the graph so we can be confident. I think so. So as we kind of trace this graph now, as I get really close to an X value of 0, do you guys agree that it looks like it's going to 4,870 about like say 0.4 or 5? Maybe like 0.45. I mean, how about this? Are you confident in saying that it's got to be more than 4,870 and less than 4,871? You now have confidence. At the very beginning, did you have that confidence? No. So this is actually, it's just shifted over. If you look at here, it's shifted over pi units. That's all that's happening there. So, all right, so let's move to this part, okay? And I don't like the way I phrase that question. I'm going to make a statement here, okay? And the statement is, we chose a window of negative 0.0001 and 0.001, 0.0001. We chose that window to ensure the limit was between 4,870 and 4,871. We chose a very small X value to say it's got to be somewhere between there, right? But if we wanted to become more exact, we'd have to choose even a smaller set of values. Again, we want to push this to 1 over infinity. That's where the definition comes in. It's the precise definition of a limit. I've taught this class now this is year number 7, I believe, at Albert Lee. I've taught it other places as well. You will be able to memorize this if you trust me, okay? You do have to memorize this perfectly for the test, and we will practice it in class together. We'll give you ample opportunity to do so. And it starts like this. The better you can draw the picture, the better you can memorize it. Trust me, that's not me saying it, that's previous students. Sure. Let there be a function. And you might have a desire to like gasp or groan or whine during this process. Just try to push that aside for a while, okay? Let there be a function. That's my function. defined on an interval, but maybe not at point A. Is everybody okay so far? Here's a function. I've drawn it over some interval, some set of x values, but as you can see, it doesn't have a value at point A. Now it could, but it doesn't have to. Then the limit as x goes to A of the function is equal to L. Now we're gonna see if you guys, this is your first test, see if you know what's going on, okay? If this is A, do you know what that is? Very good, Callan, that's L. Because that's the y value, right? That's what it's approaching. Does everybody see that? We just took a test on this, right? Do you have to have the circle filled in order for the limit to exist? In this situation, does f of A exist? No, but the limit exists. So the limit as x goes to A of the function is equal to L if, and this is where we're going to create a window. So you can see here that, you know, we created a window between 4,870 and 4,871. Our window here is going to look like this. We're going to use some fancy new letters. It looks like this. If for every epsilon greater than 0, I'll draw a couple epsilons so then you can get a better feel. So, because sometimes you see a new letter, my handwriting is not always perfect. Those are epsilons. It's the Greek letter for E. Oh, I'll show you what it is. So epsilon is going to be the y value of our window. So, for example, this distance right here is going to be epsilon. So this would be L plus epsilon. And then we'll pick a spot down here. This would be L minus epsilon. So we want to ensure that our limit is between those two values. So if for every epsilon greater than 0, there is a delta greater than 0. So I'll draw some deltas here for you so you can see a few. Yep. It's continuing. So then the limit as x goes to A of f of x is equal to L if for every epsilon greater than 0, there is a delta greater than 0. Now, if epsilon went with the y values, what do you think the delta goes with? The x values. And so here's the deal. This would be my delta value. This would be A plus delta. And this would be A minus delta. That's up to you. I would. So if for every epsilon greater than 0, there is a delta greater than 0, that satisfies the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus A is less than delta. Done. the precise definition of a limit. We needed this precise definition of a limit in order to make the rest of calculus possible. Now, I know right now it just seems like a bunch of garbage, and I could just say memorize it and show up, but we're going to spend a few days teaching you exactly kind of what this means and how it works. And instead of just using delta and epsilon, we're going to give you some values to actually put in that place. Okay? So everybody have it written down? No assignment, but let's try to draw this first example. It says consider the function f of x is 1 over 2x. What does the graph of 1 over x look like? Yeah, so 1 over 2x is going to look very similar, but it's going to look something like that, okay? It says find an interval for x values such that the y values will always be within 0.2 of the limit as x goes to 2. Sounds like a bunch of garbage to try to think through. So here's what you should do. Every time you encounter one of these problems, always start by writing down the limit, and then you'll be able to figure stuff out. What is x approaching in this problem? What is the function? 1 over 2x. So I'm approaching 2. Does anybody know then what the limit would be? 1/4. How did you get 1/4, Andrew? Is everybody clear how we came up with this information right here? Any concern at all how I got that? Great. Then it says find an interval for x such that the y values will always be within 0.2. That means my epsilon is 0.2. So what we do is we move up 0.2 and we move down 0.2. If I move up 0.2, where's that going to bring me? 0.45. If I move down 0.2, where's that going to bring me? 0.05. Any concern about that? So then we draw our lines. I want to go from 0.45 to the function and down. And I want to go from 0.05 to the function and down. Don't worry if they're not the same as you draw them out. It's okay. Is it possible for us to figure out where this function, f of x equals 1 over 2x, is it possible for us to figure out the x value that gives us an output of 0.45? How do we do that? Yeah, 1 over 2x equals 0.45. How do we find x? Cross multiply. 2x times 0.45 is going to be 0.9x. What is 1 divided by 0.9? 1.111, right? 1 divided by 0.9. So which spot did I find? Did I find the spot on the left or the right? The left. Can we find the spot on the right? How do we do that? Same thing. 1 over 2x is equal to what now? 0.05 over 1. Good. So I get 0.1x is equal to 1. Divide by 0.1, and what do you get? 10. So it's a game that we're playing. I give you an epsilon value of 0.2, and you have to find a delta value. Delta is going to be this distance. What is the distance between those two? 8. And what is the distance between these two? 0.89. You always choose the smaller of the two values. So what do I choose for delta then? 0.89. What we did is we just did a more formal version of what we explored with from the beginning. You give us an output of 0.2 tolerance. We give you an input of 0.89 for tolerance. If you want to verify that this limit exists and it's within a certain window, we say, got it. You just give us a delta value, and we guarantee that we're going to be within that. And so tomorrow we'll pick up with your assignment. You'll have a lot of time in class tomorrow to work on it and try to understand this. But we're also going to work on memorizing this piece. And then on Friday, I'll show you a little proof that we can do as well. Okay?